Let's use our vector valued function tools to analyze a common situation in motion. So suppose we have an object that's is given some initial velocity by some means, but afterwards is only accelerated by a constant force. One common situation of this is, say, we're near the surface, saying we're staying near the surface of the Earth, sort of on a local scale, and so gravity is essentially constant. What will the motion of such an object be? So to analyze this situation, let's give all the things that we don't know names. We don't know where we're starting, so let's name our starting point. Let's call that r sub 0. We also don't know our initial velocity. So let's call that v sub 0. Also, we don't know what this constant force is, but let's give it a name. Let's call it, how about f sub 0? We need to relate force to acceleration, but Newton's second law tells us the relationship between force and acceleration. So Newton's second law tells us that the total force on an object is the mass of the object times the acceleration. Remember, acceleration is the second derivative of our position function. I guess that means we need to make note of the fact that we're using r of t for the position at time t. Okay, so let's see. Newton's second law, right? This tells us how to relate what we know about the force to our vector valued function r. So let's use this. And let's divide the m to the other side. So this says that r double prime is equal to 1 over m times f. But remember, we're in a situation where there's only one force causing an acceleration, and it's this constant force that we named f sub 0. So this f right here is actually f sub 0. There aren't any other forces. Okay, well, what we want is to know what our position function is. We have a second derivative. We can just start taking antiderivatives, right? So let's take an antiderivative. There are a couple ways to think about this. We could think about this as being an indefinite integral, but to get our position in the game, it'll be better to use a definite integral. So let's integrate this, say, from 0 to t dt. On the left-hand side, when you integrate acceleration, you get velocity. So this is r prime of t. Well, it's r prime of t minus r prime of 0, right? And on the right-hand side, well, we get, so antiderivative of all this stuff in the integral on our right-hand side is a constant. So this is 1 over m times f sub 0 times, I'm being a little uncareful. So I should use a different name for this variable in this integral, because t is what I'm using for my upper bound. So maybe let me call this variable something else. How about s? So I should call this s. And we're integrating from 0 to t. Okay. Okay, so r prime of t, well, r prime is just our name for velocity. So let's write velocity at time t minus r prime of 0, that's velocity at time 0. But we had a name for that. That was our initial velocity. So let's write v sub 0. And on the right-hand side, when we plug in t and plug in 0, we just get 1 over m times f sub 0 times t, right? When we subtract and then plug in 0, we get 0, so let's not write that part. Okay, so we have a velocity function now, right? We can move that initial velocity to the right-hand side. We get 1 over m times f sub 0 times t. This f is a vector. I should be writing my vector hats. Vector, vector, all of these are vectors. Plus our initial velocity, v sub 0. Okay, well now we have our velocity function. Remember, that's really r prime. We want a position function. Let's take an antiderivative again. Let's integrate from 0 to t again. When we set up this as an integral from 0 to t, we really should rename this input variable so that we aren't using the same name twice. We're going to integrate from 0 to t on the right-hand side. Again, we should rename this input variable s, integrate ds. And then we'll do the same thing. So on the left-hand side, an antiderivative of r prime, well, that would be r. So r at t minus r at 0. And on the right-hand side, so these constants we can move outside. Notice we can even move the vector constant outside. So this is 1 over m times f sub 0, and then 1/2 s squared plus v sub 0 times s. And then we're going to evaluate this at 0 and at t. So now let's simplify all of this. On the left-hand side, r of t minus r evaluated at 0. Well, that's our initial position. That's what we called r sub 0. And then on the right-hand side, let's see, when we plug in t, we get, I'm going to write f sub 0 over m over 2m, right? This 1/2 puts a 2 in our denominator down here, times t squared plus v sub 0 times t. And then, again, when we plug 0 into this, we get 0, so let's not write down the plus 0 stuff. And then, again, we can move our initial position to the right-hand side, just like we did with our initial velocity earlier, and we get our initial position is the force over 2m times t squared plus v naught times t plus our initial position. And m here is the mass of the object that's moving around. Okay. Well, if you've taken a physics class before, a basic physics class, this will be familiar, right? This is the formula for a constant acceleration situation. But the thing to notice here is that this is all vector valued, right? So we can use this sort of analysis even when we don't have things moving along in just one dimension, like you might have seen in beginning physics courses. Using our vector machinery, we can describe more general situations. Let's look at an interesting case of that. So let's look at conservation of energy in an orbit. So suppose we have some object orbiting a much more massive central body. We're going to treat this central body as if it's a point mass located at the origin. And the object is moving around only under the influence of gravity. How does the total energy of the object change as it moves around the orbit? So if you've taken a physics class, you probably know the answer that's coming, but let's see how that result falls out of this setup. So unlike in the previous slide a moment ago, in this situation, we can't assume gravity is a constant because we aren't necessarily staying close to the surface of the body that we're orbiting around. And also, so we have this body at the origin. If we're going around it like this, we aren't staying sort of near one spot near its surface. And if you go around an object, the gravity that you experience doesn't stay constant because, well, it has to change direction at least. So we can't treat gravity as a constant in this situation. We'll have to let the physicists tell us what the force of gravity is, and this is the formula that they tell us. So I've neglected to make this F bold, so let me put a vector hat on that. Force is a vector quantity, and this is a vector formula for the force of gravity. This does assume that so what I'm using for R here is R is the position of the moving object. So we're taking advantage of the fact that the very massive central body is located at the origin, right? That's why I don't have to have some difference of vectors in the denominator here. Okay. Also, we're going to need to write down what do I mean by total energy. Well, in this kind of situation, energy comes in two flavors. There's kinetic energy. This is the energy that you get just by virtue of the fact that you are moving. And then there's potential energy, which is a general phenomenon, but in particular for us, gravitational potential energy, which is the energy that you have by virtue of where you are located. And in this situation, you have energy by virtue of where you are located because the large object is exerting a gravitational force on you. So that's why there's gravitational energy. So we have to take the physicist's word for it, that these are the appropriate formulas for kinetic and potential energy in this situation. But let's rephrase these. Let's rephrase this kinetic energy formula in terms of our vector valued functions, right? So we have an object orbiting around this central object. So its position is given by a vector valued function r, and so its velocity is given by the vector valued function r prime. So if velocity is a vector, what does it mean when it's squared like this? Well, this is a shorthand that physicists use. If they have a vector valued quantity in general, when they square it, what they mean is the dot product of that vector with itself. Right, so that's what that really means. So let's write that out. So this is kinetic energy is actually 1/2 m times v dot v. Right, so if you have a vector quantity for the corresponding scalar is the magnitude of the vector. That's usually what physicists mean. Okay. And our potential energy function, it's already expressed in terms of our vector valued function r. I noticed that I didn't say what m1 and m2 means. So m1 is going to be the mass of the moving object. And m2 is going to be the mass of the central object. And as part of this setup, remember the mass of the central object, m2, has to be much larger than the mass of the first object. The reason for that is because we're going to assume that the central object doesn't move, which, I mean, of course it does. You know, if the central object is pulling on the orbiting object, the gravity of the orbiting object also pulls on the central object. But if the central object, if its mass is much, much larger, it will experience virtually no movement from the gravity of the orbiting object. So we're going to assume that the central object stays put. Right? If we're thinking of like a satellite orbiting around a planet, right, the mass of the planet is going to be so much bigger than the mass of the satellite that there's not really any reason to think about the planet moving because of the gravity of the satellite. Okay, so let's see what happens to the total energy in this situation. So total energy, let's write capital E for total energy. That's just going to be kinetic energy plus our potential energy. And now we're going to use the formulas that the physicists gave to us. So kinetic energy is 1/2 mass of the moving object, so that's m1, times, it was v squared, but remember that's v dot v. And in fact, let's express things in terms of our vector valued function from the very beginning. So v is actually r prime. So r prime dot r prime, okay, plus the potential energy, and that's g. I didn't say what g is. G is just some constant that tells you how strong gravity is. So as far as we know, it's a universal constant throughout the universe, so it's just some number. It's some tiny number. So g times m1 times m2 over the magnitude of r, like this. Okay, so this is kinetic plus potential. Since the question is how does this energy quantity change, we're going to differentiate this, and it's a little annoying to have this magnitude of r in the denominator, so let's rewrite it like this. Let's put it in the numerator, but to the minus first power. Okay, so now let's go ahead and take the derivative of this energy quantity with respect to t. And since we have everything written in terms of our vector valued function r, we can use all of our calculus tools for vector valued functions. All right, so on this first term, when we differentiate it, well, the 1/2 m1, those are constants, so we can move those outside our derivative. And now we need to differentiate this dot product. We can use the product rule for dot products, which looks like the regular product rule. So it's going to give us r double prime dot r prime plus r prime dot r double prime. Okay. And then on our second piece, well, this g, m1, m2, those are all constants, so let's move those outside our derivative. And then, let's see, so for this part here, with the magnitude to the minus first, we have to be careful to get the chain rule right. So this is the magnitude of r raised to the minus first power. So we have to do some chain rule, right? That power comes down and changes to the power minus 2. We've got our vector magnitude in here. And now we have to multiply by the derivative of the magnitude of r. And this is something that we have worked out before. So what I'm about to write down here is just the derivative of the magnitude of r. And remember, we worked this out by taking the derivative of the square root of r dot r. So the result that we got is r prime dot r over the magnitude of r. Okay, so let's simplify this quantity, right? So this is the rate of change of the total energy. So let's simplify this quantity. So we have 1/2 m1 times, well, look, these two things, these are the same, right? The second one, because the dot product is commutative, this is r double prime dot r prime. I'm missing some vector hats. So the stuff in parentheses here is the same thing added to itself. So that's twice the original thing. So 2 times r double prime dot r prime. And I'm being a little vague about where this 2 is located, but remember, I can be vague because it doesn't matter if it's multiplying the dot product or multiplying the first piece of the dot product or multiplying the second piece of the dot product. It's the same thing no matter where we put that factor of 2. While we're simplifying, notice that this 2 cancels that 1/2. Okay, plus g, I guess minus because of this minus out here, so let me change that plus to a minus, minus g times m1 times m2, and then in the numerator, let's see, we have this r prime dot r, and then we have a magnitude of r in the denominator, but then with this r magnitude of r to the minus second, that's 2 more factors of magnitude of r in the denominator. So altogether in the denominator, we have 3 factors of the magnitude of r. So it's magnitude of r cubed. Okay. So at this point, it's a little hard to know where to go, but remember this r double prime, this is acceleration, right? And there's only one force in this whole situation, and that force is gravity. So Newton's second law says that acceleration is 1 over mass times the force, and this mass is the mass of the object that is experiencing the force. And right, this acceleration is the acceleration of the moving object. So the moving object is the object experiencing that force, and the mass of the moving object that's what we called m1. Okay, so our acceleration vector, which is really r double prime, is given by 1 over the mass of our moving object times the force, but this force is due to gravity, because gravity is the only force in the game. So this is 1 over m1 times, and now we can write down what the force of gravity is. I shouldn't put a dot there because this isn't a dot product. This is a scalar product. So the force due to gravity, and again, we're just relying on the physicists here. This is g times m1 times m2 over the magnitude of r cubed times r. Oh, I should be careful. There should be a minus sign here so that gravity pulls the objects together instead of pushing them apart. So I need a minus sign here. Yes. Okay. So we can take this whole mess. Right, this is the acceleration vector. We can put it right in there. And I realize now that I have dropped a minus sign, so if we pause for a second, this potential energy, there should be a minus sign in front of it. So, sorry, I'm missing a minus sign on my potential energy, so there should be a minus sign right here, and that means this should be a minus sign right here, and so now we have minus and minus, so this should be plus, not minus. Okay, sorry about that. Okay, so with that fixed, let's go ahead and take our expression for the acceleration and put it in here for r double prime. Remember, this whole thing that we're calculating is the rate of change of the energy, the total energy of the object that's moving around. So we have m1 times, so again, I shouldn't write a dot because this isn't a dot product. So our force, which is this whole mess, so minus 1 over m1 times g times m1 times m2 all over magnitude of r cubed times r. Okay, so this is all the acceleration vector, okay, dotted with r prime plus, let's see, g, so now I'm copying down our potential energy from up here, or that derivative of our potential energy, g times m1 times m2 all over the magnitude of r cubed times this dot product in the numerator, so r prime dot r. And then, so let's simplify this. Here we have an m1 that cancels that m1. And if you look at these two resulting terms, right, these are actually exactly the same. I know we have a set of parentheses here, but remember, because we have a scalar multiple times our vector r, we can sort of move that scalar multiple out in front of the dot product. So we could write it like this, minus g m1 m2 over magnitude of r cubed times the dot product r dot r prime plus the exact same thing, g m1 m2 over magnitude of r cubed times r prime dot r. Okay, and these two things are exactly the same, except the one in front has a minus sign, but that means that they cancel, and this all adds up to 0. Right? So, in other words, the derivative of the total energy is 0, but that means that the total energy itself is constant because its rate of change is 0. So this is the appearance of the conservation of energy, right? At least in a gravitational system, some object moving around only under the influence of gravity, well, the gravity of one central gravitating object, the total energy of the moving object is always the same. This is really why potential energy gets defined the way it is defined. In particular, why potential energy has this, it's defined with this minus sign. It's to set things up so that total energy will be constant in these kinds of situations. So what I hope you get from this example is that the machinery we have for doing calculus with vector-valued functions lets us do big calculations like this even though we don't actually know what the position function is, right? At no point did I write down a formula for what our position function r of t was. We're doing big calculations using all of our, calculus knowledge, just with a general function r of t, right? And we know some things about how r of t behaves based on the things that physicists tell us. And we can use that together with calculus to draw conclusions about how the system behaves. In particular, we drew the conclusion that the energy has to be constant.